Mhm. Okay, I think we are live. Yes. So, hello everyone, and welcome back to the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. This is webinar number 140, and we're having Admir Greljo as a speaker. Admir carried out his PhD at the University of Ljubljana in Slovenia, which was followed by postdocs at Zurich and Mainz. He then became a senior research fellow at CERN, then an SNSF Excellenza professor at Bern, and has recently moved to a tenure track position at Basel. So today, Admir will give us an update on the BE meson anomalies, focusing on their interplay with high PT observables, and we're very happy to have him as a speaker today. So before we begin, let me remind all viewers that you can ask questions and make comments via the YouTube live chat system, and these questions will be passed on to Admir as usual at the end of the talk. So please go ahead and share your screen.
Okay, can you see my slides?
Everything good.
All right. Well, thank you very much for this kind introduction. Today I want to present a work that resulted in an archive preprint, number 2212. You can see it here, and this is work done in collaboration with Jakub Salko, Alex Smolkovic, and Peter Stangl. And the title of the paper is basically "Rare B Decays Meet High-Mass Drell-Yan." So here we deal with flavor, and to start with a very general introduction, flavor is this mysterious property of matter where we have copies of the gauge representation of the fermionic fields. Actually, we've got 3 copies, and we have no idea why. It is actually, in my opinion, the most mysterious aspect of the standard model. So the standard model being quite sort of compact. It's a quantum field theory that's got certain symmetries, the space-time symmetry and the gauge symmetry, and the field content, in particular the matter fields. The fermionic ones, we have 5 gauge representations shown over here under the input symmetries, but all of them have 3 copies. This index I represents flavor, and I runs from 1 to 3. And this is the aspect that brings in complexity. So this complexity is reflected in the number of parameters of the theory. So if we just focus on the standard model that contains space-time gauge invariant operator sub-mass dimension 4, we've got 5 parameters in the gauge and Higgs sector, modulo the theta term, while in the Yukawa sector we have 13 parameters. So we have much more parameters in the Yukawa sector responsible for flavor in comparison with the gauge and Higgs sector. So if there was only a single generation of fermions, we would only have 3 parameters. So the fact that we have 13 has to do with the fact that we have 3 generations. And this thing actually proliferates a lot if you consider the standard model effective field theory. So we think of the standard model as only being a low energy limit of some more complete theory. And at low energies, the effects of this more complete theory, which sits at high energies or short distance scales, a microscopic theory at short distance scales, would manifest itself in terms of higher dimensional operators added to the standard model, so operators in the standard model effective field theory. And here we have very quickly a proliferation in the number of parameters. So considering dimension 6 operators, which conserve baryon number, there are 2,499 of these operators. And if there was a single generation of fermion, this number would have been 59. So you see flavor introduces also complexity as we go beyond the standard model. So it's not only about the counting of the input parameters of the theory, it also got to do with the actual observation of these parameters. So we have observed those in the standard model, which would be the upper part of this plot. So the charged fermion masses and mixings. And also there's some very good data on neutrinos, which could in this picture be attributed to a dimension 5. So the leading higher dimensional operator in the standard model effective field theory, we consider with this field content I'm considering here, due to the Weinberg operator. And we see some interesting patterns here. For example, in the quark sector and charged lepton sector, we see hierarchy in the masses between different generations. And the CKM mixing matrix is almost a unit matrix with small elements of diagonal elements, implying that quark, let's say quark flavor, is an approximate symmetry. And the neutrinos instead behave very differently. And so these patterns is something which is empirical, which we observe, and which we call a flavor puzzle. And we think that this is a hint for physics beyond the standard model. In the context of the standard model, we cannot address these things. They are input parameters. And hopefully beyond the standard model, there is a theory which explains these weird features. So however, these puzzle, these patterns that are observed in the fermion masses and mixings is also in some sense a blessing when it comes to the phenomenology. So patterns can be associated with symmetries, and in particular these patterns give something that we call approximate flavor symmetries in the standard model. So the fact that masses are such and such and the CKM is such and such gives rise to approximate flavor symmetries that help us understand and work out the standard model phenomenology. And well-known examples are isospin, SU3, heavy quark symmetries, the G mechanism, and so on. And they allow us to simplify the standard model phenomenology. Also, these approximate flavor symmetries can be used to formulate stringent tests of the standard model. And when we can formulate these very stringent tests in such a way that even tiny new physics effects could be detected, this would give us a window to new physics. And types of stringent tests that I'm going to talk today about, Lepton Flavor Universality, is a good example of those, on relying on these approximate flavor symmetries on the standard model. So in the standard model, flavor is approximately conserved. But if we go beyond the standard model, and let's say already at dimension 6 level, in the standard model effective field theory, there are plenty of new sources of flavor violation. So if you assume a flavor anarchy, meaning that all these coefficients are of order 1, new parameters, then the flavor observables like neutral meso mixing, charged lepton flavor violation, electric dipole moments, they already exclude new physics up to very high energy scales. And these scales, these exclusions are much more powerful than what one can achieve from high PT physics, meaning from Higgs, top, electroweak, or direct searches. So only if one assumes a flavor protection in the new physics sector, so assumes a flavor symmetry which is minimally broken by the known sources, by Yukawa coupling, Yukawa matrices, the same sources as in the standard model, these stringent bounds can be relaxed, and one can give a breathing room to new physics at the TV scale. So this illustrates the importance of flavor physics probes, and also illustrates the importance of flavor symmetries, the approximate flavor symmetries, as a tool to organize phenomenology. So this table here shows how one can use flavor symmetries to chart the space of standard model effective field theory. This comes from a work with Anders Eller-Thomsen and Aydin Palavich, where we counted the number of independent parameters, which assuming different flavor symmetry in the quark sector and in the lepton sector. So starting with the MFV case, which is shown over here in the top left corner, where we assume U3 to the 5 flavor symmetry, the largest flavor group. And here we only show the leading terms that are flavor symmetric, not including the spurion corrections. And then relaxing this symmetry systematically, so looking into the U2 and U1 subgroups, all the way down to the no symmetry limit, which is this 2,499 operators. So this gives us a systematic way to organize flavor of the SMEF, to the standard model effect field theory at dimension 6, and to study phenomenology and to study the interplay with the high PT physics, top Higgs and electroweak sector. All right, so this was an introduction to flavor, and in particular flavor beyond the standard model. And now I go into discussing the observables, where B decays that are very important in constraining short distance new physics described by, let's say, the standard model effective field theory. So rare B decays are very rare in the standard model, and they are also very well measured. So these two features, the fact they are very rare, that they are very well measured, they makes them excellent for new physics. So for instance, at the moment, we have a sensitivity to 3-level mediators with order 1 couplings and mass of a 40 TeV. For example, a Lepton quark with order 1 couplings sitting at 40 TeV has no chance to be detected directly at the LHC. It is simply too heavy to be produced on shell. However, it could indirectly lead to an effect in these transitions in such a way that they might be indirectly detected. So what's the reason behind this? Well, first of all, these are flavor changing intercurrents which do not occur at 3-level in the standard model. And also there are approximate flavor symmetries. So here we've got the G mechanism, and particularly there is a large breaking due to the top quark, which then forces this Hamiltonian to be proportional to the VTS. So the CKM involving the top quark, which is a small parameter. The CKM element is 10 to minus 2. So this has a loop plus the CKM suppression over here. So in this Hamiltonian, I have, in addition to G Fermi and these two factors, there is also a Wilson coefficient CIs and some operator O. And here I'm showing O9 and O10. So these are semi-leptonic operators between a strange quark and a B quark, lepton, anti-lepton. So on the quark side, they are either left-handed vector currents or right-handed vector currents for the primed operators. And on the leptonic side, they are vector currents for C9 and axial vector current for C10. So these two operators here are important, will play an important role later on. In the standard model at the B mass scale, the value of these Wilson coefficients can be computed from the matching this loop and so on. And this is roughly C9 equals minus C10. It's about 4.2. So a short distance new physics would correct these Wilson coefficients here. So in more details, generally how we do the theoretical predictions of weak decay amplitudes. We rely on effective field theory factorization. So the problem can be split into computing short distance contribution and a long distance contribution. The long distance is due to QCD, due to strong dynamics. And here we are dealing with computing hadronic matrix elements. For this talk, particularly important will be lattice QCD and QCD sum rules. Sorry, light cone sum rules and QCD factorization. While the short distance contribution, so these hadronic matrix elements are not polluted by they are solely determined by QCD dynamics. New physics would come in Wilson coefficients. A short distance new physics would come in Wilson coefficients. So these short distance contributions are luckily perturbative. in a sense that we could, well, okay, new physics model. If the new physics model is perturbative, then we can do a series of calculations of matching and running calculations where we go through different stages of the PFT, the standard model effective field theory and weak effective field theory. And so this program is being carried in many references recently. And for example, matching and running program of SMEFT is at accuracy of one loop level. Okay, so for B2SLL, we've got two contributions. So semi-leptonic operator is the leading contribution. So this is a contact interaction when we integrate out the loop that I showed in previous slides. And and here what we have to deal from the hadronic physics point of view is local matrix elements. So we have to deal with the form factors, and this is typically easier to deal with in comparison with this type of contribution, the one on the right hand side. So this is a contribution from 4 quark operators. So here we can generate by exchange of a W at 3 level, we can generate B, strange, charm, anti-charm, 4 quark operator. And then this can lead to a non-local matrix element between the electromagnetic current and this 4 quark operator. And so this is much harder to treat in hadronic physics in PUCP. However, this has properties, very peculiar properties. In particular, it's Lepton Flavor Universal, and it's a vector current because it goes through the photon exchange. Okay, so hunting for new physics in B2SLL decays means avoiding resonances. So this 4 quark operator would precisely give you this resonant contribution if you're sitting on if the invariant mass of the lepton pair is at the J psi, that would dominate your standard model prediction. So in these measurements that LHCb is doing in trying to search for new physics, typically they are avoiding resonances. They are looking into low Q² beams or in high Q² beams. So in particular, the latest RK measurement was done in 2 beams, in RK star, low and central Q² that are shown here. Okay. So from the experimental point of view, it is much easier to measure muons than electrons, and this is self-evident from these 2 plots. So here you can see a very nice measurement with almost no background of the muons, and while here you can see the measurement of the electrons. We have this leakage, and we've got plenty of background. So if I were to put all the observables on one slide and discuss how reliable they are with respect to experiment or theory, this would be some very simplified and sketchy plot where on the vertical axis I put experiment divided in whether we only deal with muons or we include both muons and electrons, or in the horizontal side. And on the horizontal side, I have my dividing observables on how clean they are in terms of the standard model theory prediction. So LFU observables are very clean theoretically. So these are the ratio of branching ratios, differential branching ratios in certain Q² beam of decay to muons divided by the decay into electrons. And in this ratio, many uncertainties cancel out, and there is only so the prediction for RK is basically 1 up to a % level due to QED corrections, and this uncertainty is much smaller than the experimental uncertainty. So these are very reliable in terms of theoretical prediction. However, they involve electrons, so one needs to measure electrons to do these measurements. Instead, there are many of these anomalous observables in that involve muons. And these are branching ratio of B sub s to mu mu. So this is a fully leptonic B decay, which is rather clean theoretically. It involves so in terms of the input from QCD. So one drawback is that one needs to know VCB in order to make the prediction in the standard model, but this can be dealt with. The good aspect of this measurement is that, for example, CMS is very competitive. It actually has the most competitive measurement at the moment. So it is we have more than one experiment at play giving competitive results on this measurement here, and it's generated by the axial vector currents in the standard model. Then we move next to other class of observables. These are optimized angular observables in B decays to vector mesons. And mu and anti-mu. So these are semi-leptonic decays. So we have B to K star and B sub s to phi. K star and phi are vector mesons, so one can construct a lot of angular observable distributions and take ratios. And in these ratios, a lot of uncertainties cancel. So it has a reduced form factor uncertainties, and it has cancellation of some parametric uncertainties. So these are also quite good observables in terms of theoretical in terms of theoretical predictions. And probably the hardest ones are branching ratios of differential branching ratios of different B to K star, B sub s to phi observables. All right, so what is the status of the experimental measurement? So we have anomalies in differential decay rates of B to S mu plus minus, and in the optimized angular observables. So in what is observed is a consistent deficit of muons in these decays. So the consistently smaller measurement in comparison with the standard model prediction for all these decays that have B to S, so B sub s to phi, but also for many others, B to K star, and so on. So optimized angular observables, I said, are better under better theoretical control than the differential branching ratios. And so these are fits done by LHCb. And the standard model value is here for the vector coupling C9. And they consistently prefer a smaller value, something like minus 20% or so, smaller value of the vector coupling from the one predicted in the standard model. The interesting thing is that there is a coherent and consistent pattern. So if you consider this presence of new physics in this effective coupling, then there is a consistent set of deviation. However, as I pointed already, there is a lot of theoretical debate of whether we have a good control over the non-local matrix elements. This thing that is usually denoted with charm loops, but is actually a non-perturbative effect. Whether it can mimic this large shift, actually, it's an open question. We don't know of a mechanism that could do such a large shift in QCD. So the question is whether it if it can or cannot explain this effect over here. So what really boosted the whole story out of all proportions was the measurement of previous measurements of Lepton Flavor Universality. So those are pristine observables theoretically, and one of their LHCb reported an evidence for new physics from breaking of universality at the level of 3.1 sigma. So this was actually published in Nature Physics last March. And what was very exciting was the fact that these deviations were consistent with ones in the other sector. So these LFU measurements were consistent with the measurements, with the tensions observed in optimized angular observables and differential decay rates. And this was just mind-blowing. However, unfortunately, sad news for new physics came last December. where LHCb has updated their measurements, RK and RK star. And in particular, Lepton Flavor Universality ratios are now standard model-like. So this is the plot from these two papers, which shows the measurement for RK and RK star in different Q-squared bins. Perfectly spot on of the standard model. And so the reason for this big change was in-depth revision and understanding of electron misidentification. So this solved sort of one anomaly, these LFU anomalies. Basically, it was an experimental thing. Better understanding of electron misidentification. However, we are still left with the rest of the anomalies in this sector, in B2SLL sector. So today I'm just talking about anomalies in B2SLL. I'm not talking about charged currents B2C. So to resolve these, one really needs to understand better the standard model prediction. And the bottleneck are these non-local matrix elements. And the standard method to do is QCD factorization, and there is a question about systematic uncertainties, in particular about effects that go beyond QCD factorization approach. And there have been a lot of discussion in the literature, and so I want to mention this recent work by Danny Van Dijk and collaborators, where they try to estimate the effects beyond QCD factorization, trying to making use of analyticity and unitarity of the matrix elements, and formulating this Z expansion, which is consistent with the principles of fundamental principles of QCD, and then using introducing many free parameters, and then using data and calculations at negative Q-square where they are reliable, and some dispersive bounds in order to close the fit. So what they find is shown in this plot here. And basically, they find a very similar result to QCD factorization, except for a bit larger uncertainties as one approaches the J psi. However, in terms of the tension, they find that the tension remains, that they cannot explain the effect in P5 prime in optimized angular observables to be due to this effect. Of course, there are opposing viewpoints in the community. For example, the recent work by Silvestrini and collaborators, where sort of they acknowledge the previous work in terms of estimating contributions beyond QCD factorization coming from this type of contributions. However, they point out that there could be effects that go beyond that. So something like rescattering of D mesons and so on. They do not give any calculation of these. They just point out they just point out this thing. And in fact, here they have these two scenarios. One is where they assume something like the previous work, that QCD factorization, that the corrections beyond QCD factorization are subleading. Then indeed they also see a need for a correction to C9. However, if they have a more general parameterization of these potentially new effects, which they do not calculate, but fit from the data, then they clearly don't see any need for having new physics. So it is a very difficult. I have to say it's a very difficult thing to assess at this point, and it's also not clear how fast we will make progress on this front. But it's something that is very important and a problem that needs to be tackled. All right. Okay. So what I want to do for the rest of the talk is that I want to consider. I want to ask a different question. So let's assume that QCD factorization is works well, and the corrections beyond QSP factorizations are insufficient to explain the effect in these B2S mu observables. That it is what new physics can do, in particular, given that LFU observables are now standard model-like. So how does the new physics landscape change in this respect? So we were doing, in the first part of this paper, we were doing fits in the context of weak effective theory. So a weak effective theory Hamiltonian is given in this line over here. And these are the operators that we consider. So we basically look into semi-leptonic operators, O9, O10, and others shown in this slide. Okay, so this is the first fit we want to show. This is a fit to two Wilson coefficients, C9 and C10, where we assume real coefficients, and these are the corresponding operators. And here is the preferred region from B2S mu mu, so from optimized angular observables and branching ratios, from angular observables and branching ratios, and that one is away from the standard model point, which is this one over here. Then there is RK and RK star in blue, which is now consistent with the standard model, and then there is B sub S to mu mu. Okay, so here one can see a slight tension between B2S mu mu and LFU. So here I'm only considering new physics in muons and assuming no new physics in electrons. We have in the appendix of the V2 of this paper that we put out today, actually on arXiv, we have a table like this with a lot of one-dimensional scenarios. So considering only one Wilson coefficient at a time and performing fits, again separating by B2S mu and LFU, and where one can try to see one can compare these things. In particular, the best performing ones are the LFU one, so meaning that contribution to electrons and muons is the same. And in particular, C9 LFU, C9 universal gives a pull away from the standard model at the level of 3.7 sigma. Also, C10 universal gives a good description of 3.5 sigma. And in particular, there is a very small but not very significant tension between so here B sub S to mu mu plays a role. You can compare these two numbers. I mean, they're compatible within the margins, but this is the reason why the significance is somewhat reduced in comparison, which is very marginal. However, the C9 equal minus C10 is also a possibility. I have to say that the pull of the global fit for only C9 is also not terribly bad. However, there is again this slight tension if you look into the preferred parameter space from B2S mu nu and B sub S, so from LFU, from RK star, there seems to be some small 2 sigma-ish tension between the two. So this plot here shows a combination of LFU versus LFUV. So LFU is the universal contribution, either C9 here or C9 minus C10 over here, versus LFUV, so only contribution to muons. And from this plot, you can see that new physics would like to prefer only an effect in the universal one and basically no effect or very small effect in the muons. Okay. So this plot over here shows a comparison with B to D transition. So in fact, in this work, we considered all possible combinations, B to S, either muons and electrons, or B to D, either muons and or electrons. And this is I think just a very nice comparison to see how better the situation at the moment is in B2S in terms of precision compared to B2D. So this is the standard model point, but there's a lot of uncertainty. So it's still not very as precise as the other one. Okay. So connection of all of this with high PT. So if we are working in the context of the standard model effective field theory as a framework to describe a generic short distance new physics, then we also expect to have correlations between different observables at low energies and so on. So a useful tool is to construct a global likelihood, and this is a program that's done in these references, where one is trying to put all the data together and construct a global likelihood as a function of the Wilson coefficients, and then do fits. So here, for example, one includes flavor data, electric precision observables, and so on. So the work that we have done in this reference here was actually the bulk of this work was to actually implement high mass Drell-Yan in Flavio and do a systematic study in the context of standard model effective field theory. So here we consider some heavy new physics that is heavier that cannot be produced on shell in proton collisions at the LHC. It's heavier than that, and then its effect will lead to a contact interaction, let's say a semi-leptonic contact interaction, which then would be observed in the tails of the high mass Drell-Yan, so producing lepton pairs at high energies. So this plot over here shows a distribution in the number of events as a function of the dilepton invariant mass. And this here is some Z prime benchmark, which is very heavy, more than 5 TeV. So it cannot be observed as a peak. It's too heavy. And however, in this region over here, around below so in the region below 2 TeV, actually you can see that it's well described by an EFT. So EFT can very well describe this negative interference of this benchmark with the standard model and have some sensitivity in these tails. Okay. So what we did was basically to consider the latest data from Atlas CMS and so on, and on the neutral and charged current Drell-Yan, and put a limit on effective field theory. So this plot over here, for instance, shows a bound on the effective scale, so lambda over square root of the absolute value of the Wilson coefficient, as a function of the highest bin that we include in the analysis. So in this way, we can have sort of a control of effective field theory expansion. So if we consider, let's say, the highest bin to be about 1 TeV, we already saturate the sensitivity, and this is applicable for new physics heavier than 1 TeV. So different curves here represent different benchmarks for new physics. So these are the operators shown in these shown here. For example, this 1,1 label is for the quark flavor, and this is valence quarks. And 2,2 label is for lepton flavor, which is muons. So this would be, for example, UU bar going to DD bar, UU bar going to mu plus mu minus. And here we have BS. So it's BS going to mu. And this is BB bar going to mu. And so you can understand also different sensitivity. The first 3 are due to valence quarks. The last 2 are due to C quarks. And C quarks are suppressed, have suppressed parton distribution functions with respect to the valence quarks. Nonetheless, the scale that one can achieve, they are going in several TeV range, which can be very useful for many models. So the prediction of Drell-Yan in the SMEFT there are at tree level, there are a number of operators that many operators that contribute. The leading effect is due to 4 fermion operator. This amplitude scales with the energy squared, while other operators they give softer dependence on the energy, and they are sub-leading. So these would be operators that correct gauge boson vertices, and they are also constrained from let's say on-shell production and so on. So we consider only the 4 fermion operators for this exercise. However, still there is a huge number of them. So if one imposes no symmetry, there is like 855 operators, and with imposing flavor symmetry, there are less. So this is the counting shown in this table. Okay, so here we are looking into first set of results shown in this table. So here we are considering one operator at a time. So we switch on at some high energy scale, let's say at 1 TeV. We switch on one operator and one Wilson coefficient. So here it would be to B to D electron E plus E minus. So we consider all possible cases, B to D, B to S, electrons and muons, and all possible semi-leptonic operators, and switch only one coefficient at high energy scale, and then see a complementary bound between Drell-Yan and B decays. So here you can see in this table, due to lack of time, I won't explain it in details, but the main point here is that in such a case where we really have like just a minimal operator that contributes to B decays, then the constraints from B decays, rare B decays, are by far the most stringent. So the constraints from high mass Drell-Yan do not compete, and this is as expected. However, in realistic new physics models, we typically do not get only one flavor only one coupling switched on, another set to 0. For example, if we have minimal flavor violation, a more involved structure, then in that case, the Drell-Yan becomes very competitive. So here is an example of two-dimensional fit. So the horizontal axes are the singlet operators. So one here stands for SU2 singlet contraction between leptons and quarks, and triplet is the vertical axis. So it's a triplet contraction between lepton bilinear and the quark bilinear. So here actually I am I'm saying that this flavor tensor has a minimal flavor violation. So the first term would be flavor symmetric, a delta function. And the second term would have insertions of the Yukawa couplings, YU and YU dagger, for instance. And let's say I stop my MFV expansion at this point. And now I'm left with 2 independent parameters, this one and that one, for the 2 operators. And so this plot here is when I assume that 2 of them are equal, so that the leading term and the next leading term, they have equal sizes. Also for both for triplet and for singlet operators, and this is the fit. So here you can see in orange B to S mu mu, and the high mass Drell-Yan is actually very close to the origin. Let me zoom in. So if I zoom in here, you can see constraints from high mass Drell-Yan in green and purple from neutral and charged currents, and in orange is B to S mu mu. And there is a tension between these 2 regions of parameter space. So actually this tension is even worse if you go to the linear minimal flavor violation case. So linear MFV is when this term in the expansion is actually even smaller than this term. So this, because if we want to have a meaningful expansion, Yukawa top is another 1 parameter, so there should be an extra suppression in these terms. So if we go to that limit, this tension increases. If we flip the sign, then the tension is reduced when we have coefficients of the same size. But again, if we go to a linear minimum MFV limit, the tension will come back. So this was just an example to say that in realistic models there will be a competition, there will be a complementarity between constraints from rare B decays and from high mass Drell-Yan. How much time do I have?
15 minutes would be okay.
Okay, thank you. All right, so this is the last part of my talk where I want to give a few model examples to illustrate these points. These will be LFU models, so the models that predict the same effect in muons and electrons. I will consider generating B2SLL local operator at the UV matching scale at 3 level. So a 3 level generation of this operator at high energy scale. And this is not the only way. One can consider other options, for example, loop generated or maybe RG generated and so on. However, this is the let's say the simple and the starting point one can do, and here one can do it with an exchange of a Z prime or with an exchange of a Lepton quark. So a Z prime is the common Z prime models, completions of a Z prime are typically Lepton flavor universal. So this is like example of this would be gauging B minus L, and typically Z primes would couple universally to electrons and muons. Another example would be that we will use is an example of a coupling to 3B3 minus L, where B3 is the barrier number for the third family. And here we will have a reduced constraint from high mass Drell-Yan, as I will show later. Lepton quarks instead are not typically Lepton flavor universal. So if you have a single Lepton quark, a single Lepton quark field which couples both to, let's say, electrons and 2 muons, then there would be charged Lepton flavor violation. So if a Lepton quark couples both to electrons and 2 muons, looking at this diagram, so both to electrons and 2 muons, a single representation, then there would also be decays to decays to E plus mu, so charged Lepton flavor violation, where one closes the loops, one gets mu to E gamma or mu to E conversion and other processes. And we have a discussion on this, and it turns out that a single Lepton quark couples both to electrons and to muons doesn't work. So an LFU Lepton quark would be something else. It would be to at least have a doublet of Lepton quarks. So here I'm considering this representation, color triplet, weak triplet with a hypercharge 1/3. So color anti-triplet. So this is called typically S3 in the literature. And I consider 2 of them. So one will be charged under the electron U1 and the other one under the muon U1. So carrying electron and a muon number. And there will be a Z2 symmetry, like a parity that exchanges electrons to muons, a Z2 parity for Lepton flavor universality. So such a symmetry will ensure mass and coupling degeneracy, and it will ensure that there is a same contribution. When one integrates out the Lepton quark doublet, there will be a same contribution to muons and to electrons. It will ensure Lepton flavor universality. So these 2 models would match on these 2 plots. So in particular, Z prime would give C9 universal. So a vector vector coupling, typically a vector coupling, the ones like B minus L would give you vector coupling with leptons. And a leptoquark would give an axial, it will be V minus A, so left-handed vector couplings, so left-handed interactions. And both of them are okay, as you can see from these two plots. There are a lot of complementary bounds, in particular for Z prime. So Z prime gives other three-level effects, like it can give neutral meso mixing at 3 level. So if one exchanges it between B bar S, one can get BS bar. So delta F equal 2 transition. But now, since that prime couples also to electrons, it can also give a contribution to lepton production at Lep2, for instance, on the four lepton interactions of contact interactions of 4 leptons, which are constrained very well at Lep2 if one also couples to electrons. So you can see that B2S LL diagram is actually the product of the two couplings, the red and the blue. And the red is constrained from B sub S mixing, and the blue is constrained from Lep2. And so you see that this is very generic, irrespective of the completion of the Z prime model. So should apply no matter how you complete the Z prime. So these are two examples of the completion, U1B minus L and B3 minus L. So what you see on these plots are different constraints from different observables. So the orange is B2S mu mu. Blue is delta F equal 2, so meso mixing. And yellow is Lep2, and LHC, high-mass Drell-Yan, is green. So these are the preferred regions at 1 sigma by different measurements. So the vertical axis is kappa, and kappa tells you how much is the coupling of a Z prime to strange and bottom. So BS Z prime coupling in the units of VTS. And then the horizontal axis is the ratio of the mass of the coupling, or the mass of a Z prime over the gauge coupling. So everything is characterized by two parameters. In the case of a heavy Z prime, above the above the direct searches. Actually, if the Z prime is lighter, then typically the bounds from resonance searches are very stringent, unless it's very, very, very light. So here I'm considering the case when it's heavy, in such a way that some model EFT applies. So what is the point of this plot? So here kappa equals 0 would you see that B2S mu anomalies prefer non-zero kappa, and there is no regional parameter space where all of these meet. So for example, this is the region where B2S mu and delta F equal 2 are compatible with each other. This is the region, the decoupling region of where masses are heavy and kappa is 0, is the region where delta F equal 2 agrees with the high mass Drell-Yan, but you see the tension between them, and you see the tension between them and between that region and this region over here. So the difference between these two plots is the fact that on this plot over here, the constraints from high mass Drell-Yan is relaxed, because this is a coupling to 3rd generation of quarks. So a baryon number for the 3rd generation. So here indeed the high mass Drell-Yan can be compatible in this region over here with beta mu and delta f equal 2. However, we still have a bound from Lep2, which is the same because it just comes from the coupling to leptons. Okay, so that's a general conclusion for Z primes. And for leptoquarks, actually leptoquarks are easier. So they only give at 3 level 2 quark and 2 lepton operators. And they give delta f equal 2, so 4 quark and 4 lepton operators, like the Lep2, they give it at 1 loop. So those are suppressed. And therefore, this kind of leptoquark, the LFU leptoquark, can easily give this effect, which is compatible with other complementary searches. And here is the preferred parameter space. So you can have, let's say, for kappa equal 1, -1, which is natural value for this parameter. The mass of the leptoquark over lambda. Lambda is this coupling here. You see, lambda I are the couplings to quarks and lepton. Lambda I are the different quark flavors. And if you assume this structure, namely that we have a VTD, VTS suppression, this is a U2 structure in the quark sector. For lambda of order 1, this would require something like a leptoquark of, let's say, almost 10 TeV, which is also okay with the direct with the direct searches. Okay, so just to sum up what I did. So for the Z prime, before the RK update, the common models were the one that exclusively couple to muons, and now the data prefers some kind of Lepton Flavor Universal physics. And if we have a Z prime, which is Lepton Flavor Universal, it also means that it couples to electrons. So we have important bounds from Lep2, and somehow this favors Z prime models. Leptoquarks, instead, they if we have a single leptoquark that couples both to electrons and to muons, then we have issues with charge lepton flavor violation. So we have to have this delicate global symmetry, which we have a pair of leptoquarks that are mass degenerate and same couplings. One couples to electrons, the other one to muons, and in such a way that in that case, which can be written, okay. In that case, we could have this. We could have this solution. All right. So instead of concluding, I will give you the outlook. This is not by no means the end of research in rare B decays. It is clearly a disappointing in terms of for new physics. The release, it also pushes the research in different direction and gives priorities on different things, which is okay, which is good. And you see the program of experimental flavor physics in the upcoming decades. So we've got LHCb running, and we have Bell2, which will be an important player in this field, and other things for charm physics and so on, and for tau physics in particular. And there is also a lot of work for theoretical physicists. And the main job, the core problem, is to do precision calculations of flavor observables, both in the standard model and also beyond the standard model, in particular in the context of effective field theory, in the standard model effective field theory and weak effective theory, and trying to combine different observables. So the goal is to match the foreseen experimental precision, and then hopefully, probably it didn't happen this time, but hopefully it will happen at some point, that we discover a deviation from the standard model prediction. And hopefully this will also lead us towards understanding the big open questions of flavor puzzles And that's it. Thank you.
Thank you very much for this great talk. So now we open the question round. So we encourage viewers to add their questions on the YouTube chat. However, since we usually there's usually a lag between the talk and YouTube and the YouTube transmission, we'll have questions first from this audience. So I have a couple of questions, but I don't know if Roberto would like to begin.
Yes, I have a question. I mean, one of the questions that I was wondering if with the effective operator, can you get some insight about maybe the discrepancy in the W mass or something like that? I mean, how which operator will be compatible with a possible?
Yeah, it's a different. So the W mass are a different set of operators. So here here we are looking into 4 fermion operators, semi-leptonic operators. W mass would be a different operator, like a T parameter. Sure, there are models which put these things together, but
okay, so
not very convincing in my opinion.
Yeah, what happened with the anomalies?
Yeah. So with anomalies, well, it is always very difficult to bet against the standard model. This is clear, but it's always good to look at these things in more details.
Yeah. The question was, even though you were discussing, especially in the case of Lepton Flavor Universality, I mean, yeah, but there are other type of U1 symmetries that the people used to use, like the mu minus tau, something like that. That is mostly for the leptonic sector, but this kind of symmetries that are universal would also match in the description that for the standard model. I mean, to be within the data.
Yes, so those would be rather tricky now, because those give corrections to RK. So one has to look into details of the model. Maybe they fit within the margins of. Let me show one of these. You see, RK now is standard model-like, so those models would violate Lepton Flavor Universality. But again, there are error bars on that statement. So the part of the discussion that I did was to assume that RK exactly 1, so that there is no contribution, and then I discussed models. Of course, the data is not perfect. We saying that it's 1, so we have some space for it. So it has to be analyzed. One should see. Also here, when I say slight tension, so this is just 2 sigma. And in fact, if you also now look at these fits, so B2S mu mu is 3.7 sigma. So this is actually a bit disappointing to what this used to be. Like if you look at these fits from before the update, these were all above 5 sigma. Okay.
And now they.
Yeah. Okay. Now this is not all of them. But this one was above 5 sigma. So there was now these are yeah.
Yeah, and one last question: when you were presenting different kind of, I mean, for this case, Flavio, is this Flavio is open?
Yes, this is an open source package. Yeah, this is an open source package, and you can.
Is it Python, Mathematica, or something?
It's Python package. Python. It's based on Python. Yeah.
Okay, cool. Okay, I don't know, Joel.
Yes. There are no questions yet on the. Oh, hang a second. We just got a question. So from ER4000. So the question is ER4000 is the name. No, it's the username.
Okay.
So the question is, the sensation is that the flavor anomalies are going away. Is that feeling right?
Of course.
I guess.
Yeah.
Well,
if that was not clear from my talk, then I totally failed in.
Right. So.
But it's important because it's progress. So we are making progress.
Yes.
We are solving
Yes.
problems. We are solving problems along the way and making progress.
Yeah, and it was a path that had to be followed, right? It had to be followed.
Yes. I think we have no. We have no. I mean, a better alternative than look things into more details, do better measurements, and do better computations, and then hope that the two would disagree eventually.
Yeah. So the main thing here is that if you want to describe the angular analysis, the decay rates, now you do not want to go to the flavor to the Lepton Flavor Universality breaking operators because of RK. So of course the conclusion to that is that now you need two scalar leptoquarks for addressing these other anomalies. Well, before you needed one, right? You needed one scalar for the muon and one scalar for the tau that you haven't touched. But so now it's two. So if you wanted to also address the RD anomalies, you would need three scalar leptoquarks. Is this correct?
Yes. So it also means like what does address mean? Because if right. I look at these the models that I presented in the last part of my talk, they were hypothetical, saying what if RK is exactly 1? So there is no physics in that case, what would be the landscape of new physics models? And indeed, in that case, one needs to have a flavor doublet, two leptoquarks, which mass degenerate coupling, should have some kind of global symmetry structure. The current data, again, is not saying that RK is exactly 1. And if you look this Wilson coefficient here, which is just 2 muons, the pool of B2S mu is 3.6 sigma. This is very bad because it's LFU, but combined, it's not horrible. Sure, there is a small tension. And now we are also talking about 3 sigma effect. Okay, so this universal guy is 3.7 sigma, the one that I explained in the last part of the talk, which predicts no contribution to LFU. Okay, it just predicts to LFU V observables to RK and RK star. It's purely LFU, and the fit is 3.7 sigma. The charge current anomalies are also 3 sigma. Yeah.
Right. So no, it's a problem, this thing about the Lepton flavor violation, right? Because if you want, right, I mean, before you could avoid that with the leptoquark.
No, but I'm saying if you are willing to hunt this 3 sigma anomaly, then a leptoquark which couples only to muons and not to electrons would fit the first line. Sure, it would have a small tension between RK and B sub S2 mu mu, but this tension is at the level of 2 sigma. If you assume, as I assumed in the last part of my talk, that RK is exactly 1, which is not, I mean, maybe that would be the development in the future. Maybe this tension will remain and we do not figure out how QCD can solve this. but RK measurements become better and better and better and closer to unity, then one would have to go with some LFU new physics. And also, like the models that I explained applies only to 3 level. There are other options, for example, which would be a bit more interesting for, let's say, in the context of RD star. So one can have a, let's say, a purely third generation operator like BB bar tau tau, and then close the loop, attach a photon, and get an RG effect. Right. Through so B char to SU2 operator mixing and get B2S mu. But of course, this would be effect which is suppressed compared to 3-level effect. So for the 3-level effect, I think it's interesting that if you really want to have a Z prime model, then and you really want to have put RK to 1, then you get these complementary bounds from Lep2, which I think is something new that before you didn't have, because before you just couple to muons, so you don't have Lep2.
Yeah, exactly. Yeah. So then, okay, I think you have solved my second question, which was that I mean, if this RG effect, this operator mixing, from this operator mixing, you could say something about the operators solving with the quotation marks the RD from the constraints from RK, right? Because from what I understand, whatever new physics you put on that modifies RD will also affect
that effect is Lepton Flavor Universal, because it goes through the photon, which is good.
Oh, I see.
That effect is Lepton Flavor. Although the numbers do not work completely, you know, they are not spot on, but indeed, if you consider a contribution to B2 char tau neutrino, and you consider the SU2 counterpart, which is B2 strange tau tau, and you close the tau loop and attach a photon, you will get LFU, so C9 universal.
Yeah, and that will not affect our case, so that means
that will not affect
great.
RK, which
so
is
then,
good in this context.
Excellent. Okay, great. Let's see, we have any other question. So have people thanking you for the talk? 2 people are thanking you for the talk.
Thank you for the patience.
That's great. It's been very good. It's been very nice talk. One last question. Just you did mention that your standard model effects depend on VCB. Could you remind me what's the status of VCB? Because there was a long issue with the exclusive and inclusive
versus inclusive. Yeah,
I don't know what's the status of that and how it affects everything that
the prediction of B-sub-S to mu. So this is basically converging on the inclusive, and the prediction that we are having is closer to the inclusive VCB. Okay. When I said that one could use, tricks to go around VCB here, for example, one can construct a ratio of this with the delta MS being the mixing of B-sub-S. Yeah. Where VCB would cancel in that case.
Right. So then VCB is part of the fit with
yes. So in Flavio, VCB is part of the full fit. So it is fitted together with the Wilson coefficients. I see, and that's why you say that it's closer to the inclusive one, right? Yeah. Okay. Great, fantastic. So that's it, I guess. I don't know if Roberto has got any other. There are no more questions from the audience.
Right. So thank you very much for the talk, and thanks everybody for joining. And please stay tuned, as next week, in 2 weeks' time, we will have Valerie Domke giving a talk. So thank you once again, Admir, for the wonderful talk.
Thank you very much for having me.
See you around.
Bye.
And we are no longer